Hey guys, so we're going to continue our discussion today of function relationships, but we're going to add something new today that I like to call concavity. Okay, so we've got three different types of curves here. Two of them have concavity, one of them does not. So I hope it's pretty obvious that you can tell that this curve right here is the one that we consider to have no concavity. So this is no concavity, while these other two are concave. This one, because it's kind of curving in an upward motion, we call this one concave up, while over here it's kind of going downward. We call this concave down. Now, there's some other important features about functions that have concavity and not. So overall, we could easily determine that this is a linear function. Okay, so let's say that f of x is linear. Okay, what do you know about the derivative of a linear function? If you take the derivative of a linear function, it's always going to be whatever your slope is. It's always going to be some constant. Okay, so you just get some constant value. Okay, let's look at this guy right here. We don't actually know what kind of function it is. Maybe this is an exponential curve, actually like exponential growth, whereas this is the reflection of an exponential function, okay? So I don't know what the curve is. I don't know what f of x is. But what I do know is that if I were to look at all these little tangent lines right here, what do you notice about your tangent lines? Okay, so here, if I were to draw my tangent lines on this first one, my slopes are all identical, and so I get f prime of x as a constant, okay? Here, I know that f of x is increasing, but I don't really know what else. But if I look at f prime of x, I look at my slope. So my slope here versus here, okay, as I move to the right, my slopes are getting a little bit higher. They're increasing. So in this case, f prime of x is increasing. Okay, do you guys see that? Because if I were to draw a bunch of little tangent lines, my slopes are getting progressively higher. Well, let's look over here. I don't really know what to say about f of x for sure. I mean, I guess I could say f of x is concave up and concave down. These are understood acronyms for concavity, by the way. Here, if I were to look at my slopes of my tangent lines, now what do you notice is happening? My tangent lines, the slopes start out kind of steep, but then they kind of start to flatten out. So those are actually decreasing. Now, whenever we talked about increasing and decreasing in the past, before, if I were to look at just this function by itself, and I were to say that f of x was increasing, that meant directly that my derivative was positive. Okay? On the flip side, here, well, actually my function is still increasing. So my function is still increasing over here, which means my derivative is still positive. So increasing, this is still positive. Okay, so that's the relationship between function and derivative. Well, if I think of the derivative itself as its own function, what do you think is happening on the next phase down? So if I start with my derivative, the derivative of that would be my second derivative. Okay, and we just put, we've done second derivative before. We take the two little quotes right here. Well, so now if I know that my first derivative is increasing, that must mean my second derivative is positive. Okay, and I get this relationship because remember, if my original function were increasing, that meant my derivative was positive, or vice versa. So now if I know that my derivative is increasing, that means its derivative is positive. On the other side, if I know that my derivative is decreasing, that means my second derivative is negative. Okay, and you're thinking, well, why is that important? That's important because now we have this new relationship that if your second derivative is positive, it tells you that your function is concave up. If your second derivative is negative, it tells you that your function is concave down. So that's a new relationship we haven't really talked a lot about up until this point. Okay, where does that come into play? Like, why do we care? Well, let's look at the function x squared minus 1. Okay, so what we've been doing the past couple of days is we've been talking about our relative extrema and all that good stuff. So the function x squared minus 1, visually, you have parabola transferred or translated down 1 unit. So it looks like this, crosses here and here at -1 and 1. Okay, so overall, if I look at this graph, okay, it changes from decreasing to increasing. Okay, which means if it's changing from decreasing to increasing, that means my derivative changed from negative to positive, so I have a relative minimum right here. Okay, well, another cool thing about this is now I can start to look at my second derivative and how my second derivative can actually help me find my relative extrema. So let's say we went ahead and started this process of finding relative extrema. Okay, so whenever we do this, we always start with finding our critical numbers. So f prime of x is equal to 2x. I set that equal to 0, so 0 equals 2x, x equals 0. F prime of x is never undefined. So the only critical number I have right here is x equals 0. Now, knowing what the graph looks like, I know that this is going to be a relative minimum. Okay, couple of ways to prove that. We look at our first derivative. Okay, we look at the changes in that, but now I can also look at my second derivative. Okay, so what I want to look at here, okay, well, actually, let's go ahead and look at the first derivative. So we've got the interval from -infinity to 0, 0, 0 to infinity, and I already know that my first derivative is equal to 0 here. If I were to plug in a negative, I'm going to get a negative, so negative, positive, f is decreasing, increasing. This is a relative min. Okay, if I wanted to, I could actually shift all that stuff down and come up with a new, or I could actually draw a whole new chart. Let's start with the whole new chart. Okay, I'm going to keep my same critical number. So I've got -infinity to 0, 0, 0 to infinity. Okay, I want to look at what's happening on my second derivative. Okay, so that means I plug in numbers into my second derivative. So, running low on room here. Well, not really. Let's see. If my first derivative was 2x, my second derivative is just 2. Okay, so my second derivative is always 2. No matter what my x value is, it's always 2. So if that's the case, that means my second derivative is positive. Means this is also positive. Okay. F prime we know was, let's see, we said negative, positive, which determined on F that this was a relative boop, boop, minimum. Okay, is equal to 0 here. Now, here's the cool thing. Okay, this number right here is a critical number. Yes, yes, because that's where my derivative is equal to 0. Okay, what I can do is I can evaluate my second derivative at that critical number and determine if it's positive or negative. So if I have f double prime of 0, or I'm sorry, yeah, f double prime of 0, well here, f double prime of any number is a positive, okay? Because this right here is a positive number, that tells me that my graph, my function, is concave up at my critical number. If my function, I know, is concave up at my critical number, well, that means this has to be a relative minimum. Okay? If my critical number, I plug it into my second derivative and I look to see what's happening. Because it's positive, that tells me my function is concave up. So that means this critical number is a relative minimum. We already knew this from the first derivative test. This is just an alternate way of determining your relative extrema. Okay? Let's try one more, because I think that might be a little bit confusing. Let's just look at negative x squared minus 1. Okay? Very similar function, but what's different about it? Well, it's shifted down, okay? But if I were to look at the derivative, so f prime of x, now it's going to be negative 2x. So I look for my critical numbers. So 0 is equal to negative 2x. X is equal to 0. Still, again, f prime of x, never undefined, okay? Now I'm going to look at my second derivative. If this is my first derivative, my second derivative now is going to be negative 2x. No, not negative 2x. Just negative 2. My bad. Just negative 2. So now my second derivative is always negative. It's always negative. So if my second derivative is negative, that means, so second derivative is always negative. That means f prime of x is always decreasing, but it also means f of x is always concave down. Well, if that's true, this is a critical number. I know that my function is always concave down, therefore this must locate a relative maximum. Okay, I could do the whole chart and all the stuff that I did in the last page, but does that kind of make sense as to how we bring this all together? So if your relative, well, okay, let me back up. If you plug in your critical numbers into your second derivative, okay, you plug in your critical numbers into your second derivative. If it's positive, that means your graph, go back, means your graph is concave up right here, so you have a relative minimum. If you plug it into your second derivative and you get a negative, that means your graph is concave down, which locates a relative maximum. Okay, I hope this makes sense, but let's put this all together. Okay, this is called the second derivative test. Now, in general, the second derivative, just by itself, the non-test, if you take out the word test, second derivative determines concavity. Okay, second derivative test determines relative extrema. This is going to be a point of contention and confusion at some point throughout this year. It has every year, but I'm hoping it gets better this year. Second derivative test is for extrema. Ooh, I should say relative extrema. For relative extrema. In general, just the second derivative by itself is for concavity. Because I can look at intervals of concave up and concave down, but then I can also plug it into the, like plugging critical numbers into the test to determine my relative extrema. Okay, so here's the actual test. So f is a function such that f prime of c is equal to 0, and the second derivative of f exists on an open interval containing c. Cool, we get that. If your second derivative at that value is positive, then f has a relative minimum at f of c, or at c f of c, which makes sense because if the second derivative is positive, that means your function is concave up, which means you have a relative minimum. On the flip side, if f double prime of c is negative, then f has a relative maximum at c f of c, which makes sense because your function is concave down, so you'd have a relative maximum. So relative min here, relative max here. Okay? If you plug in your critical number into your second derivative and you get a 0, the test fails. That is, f may have a relative maximum, a relative minimum, or neither. We don't know. In that situation, you actually can't use the second derivative test and you need to go back to the first derivative test. So the second derivative test, you're going to find situations where it just comes in handier than the first derivative test, because sometimes that first derivative test can be a little bit cumbersome. Again, it's hard to know that for sure right now because we're learning this all at once. you'll get better at it, okay? But in the event that you try the second derivative test, you plug in a critical number into your second derivative and you get a 0, test fails, you got to go back and try something else. And you honestly, you might not even recognize that it wouldn't fail until you tried it. You know, just like they say, if at first you don't succeed, try again. So try it, fails, try something else, okay? So the whole world of math. It's what we do all day, every day. Okay, so I want you to determine the intervals on which this graph is concave up or concave down. Now, this is kind of switching gears a little bit, but we're going to get back to that relative extrema. So now we want to talk about, well, where is this graph concave up and concave down? Because we see this word right here, this is your first clue that you need to be focusing on your second derivative, okay? So what I want to do here is determine where this graph is concave up and concave down using my second derivative. Well, to do that, got to start with the first derivative. So f prime of x. Oh, yes, another opportunity to use a chain rule. I know you guys are so excited about that. The derivative of e to the negative x squared over 2 is e to the negative x squared over 2 times the derivative of this. So this is going to be negative 2x over 2, correct? Which is just, you know, negative x. Okay, clean that up just a smidge, and you have the derivative is negative x e to the negative x squared over 2. Okay, well, that is our first derivative. I need to determine concavity, so I need to do my second derivative. More chain rule. Oh, and we get to use the product rule. So, oops, I wrote f double prime. I did not mean to do that. I was getting ahead of myself. Prime. Okay, now I want f double prime of x. I was just so excited to get to the second derivative, as I'm sure you are as well. So, derivative of the first, negative 1, times the second, e to the negative x squared over 2, plus the first, times the derivative of the second, which, oh, we already know what that is because we've already taken the derivative of that. So that's going to be times negative xe to the negative x squared over 2. Okay, so let's see if we can clean this up just a smidge here. So we're going to have negative e to the negative x squared over 2. Negative times a negative is a positive, so plus x squared e to the negative x squared over 2. Okay, so on the right track so far. Now, remember when we changed from increasing to decreasing back when we were looking at the first derivative, we looked for where the first derivative changed from positive to negative, but it had to go through 0. Well, to change concavity, in order for you to determine concave up and concave down, you need to look at where your second derivative does the same thing, where it changes from positive to negative and goes through 0 to know where that actually changes. So the first thing we're going to do, or I guess not the first thing, but the next thing we're going to do is we're going to set our second derivative equal to 0. So negative e x squared over 2 plus x squared e to the negative x squared over 2. Okay, I'm going to set that whole thing equal to 0 and see if I can factor this out. Let's see. So I'm going to take out a negative e to the negative x squared over 2. That leaves me with a 1 minus x squared. Okay. And so then I'm going to need to set each part equal to 0. So negative e to the negative x squared over 2 is equal to 0. And then 1 minus x squared is equal to 0. Well, this is e to the, okay, this is a reflection, actually a double reflection, like you've got, it's exponential growth, because e to the x is an exponential growth curve, but you've got a negative up here, so that reflects it over the x-axis. You have a negative, sorry. This reflects it over the y-axis. This is going to reflect it over the x-axis. So basically, though, I have a reflection of an exponential growth curve that never crosses 0. So this right here has no solution. Okay, there's not a single number I can plug in for x that e to that number would give me a 0. So that's no solution. So x is equal to 1 plus and minus 1 over here, essentially. That looks like a weird 4. So let me just, x is equal to plus and minus 1. Okay? So the only numbers where my second derivative is equal to 0, our x is equal to plus and minus 1. Okay, so just like we made a chart with our first derivative, we're going to make another chart with our second derivative. Okay, I'm going to go from, this was not on a closed interval. No, this was over the entire line. So we're going to go from negative infinity to negative 1. Let's talk about negative 1. Negative 1 to 1. Talk about 1. And then 1 to infinity. Okay, and we're talking what's happening on f double prime of x now. Ooh, the charts are getting slightly cleaner. We'll see. So I know that my second derivative is equal to 0 here and here. We already determined that up here. Okay, I need to know what's happening in between. So let's look at f double prime. Let's go with negative 2. Okay, f double prime of negative 2, if I were to plug that in up here, okay, it doesn't matter what's up here. This number matters like what's happening right here. And actually, I'm not going to lie to you, I like to work with the factored version of my second derivative. So like my second derivative here is negative e to the negative x squared over 2 times 1 minus x squared. I like working with a factored version because to me it's a lot easier to tell is it positive or negative. Again, I don't need to know the actual value of my second derivative at negative 2. I just need to know, is it positive or negative? So if I plug in a negative 2 right here, okay, this is going to be some stuff. It's going to be a number, but basically all of this is going to be negative because of this negative right here, okay? And so then if I plug in the negative 2 over here, let me show you what I'm talking about here. F double prime of negative 2. This part is going to be a positive times 1 minus negative 2 squared would be positive 4, but 1 minus that would be a negative number. So positive times a negative would give me a negative, okay? Is everybody following here? In my notes from last year, I showed that that should be a positive. So let me pause for a second and regroup. What did I miss? What did I miss here, guys? Plug in a negative 2. Hang on. I figured it out. I had to pause, come back to it for a second, and then I immediately looked at it and was like, oh my gosh, Murphin, you are ridiculous. You even said negative out loud. I remember saying negative. But then I wrote, this is a negative. This is a negative. So that's positive. All is right in the world again. All right, here we go. F double prime of 0. E to the 0 is 1. Great, fancy, wonderful. Either way, this whole thing is going to be a negative, not a positive. Don't write positive. It's negative. That's my note to myself, by the way. And then we're going to have 1 minus 0. That's a positive. So this whole thing is negative. Okay, so this f double prime of 0 is negative. Okay, and let's look at f double prime of 2. Again, let's see, f double prime of 2. All that's going to be a negative times 1 minus 4 is going to be another negative. So that's going to be a positive. Okay, so if that is the case, here's what's happening. Okay, my function, so this is my second derivative. That means I can look at my original function. Since my second derivative is positive, my function is going to be concave up. Since my second derivative is negative, my function is going to be concave down. I can spell. Concave down. Okay, and then back over here, concave up. So then the intervals of where it's concave up, let's see, f of x is concave up on negative infinity to negative 1 and 1 to infinity because f double prime of x is positive. F of x is concave down on negative 1 to 1 because f double prime of x is less than 0. Perfection. All right, so we wanted to know where the function was concave up, concave down. Had a couple of math mistakes on my end. It happens sometimes. Don't worry. But I hope that makes sense on how to determine concavity. Okay. So let's look at the next thing. Question. Well, okay, so then what do we call that point where the function changes concavity? This is actually going to be called a point of inflection. Aha. Okay, it's called a point of inflection. Where the function changes concavity is a point of inflection. Okay, what is happening at this point of inflection? Well, let's go back at the slide. Okay, where would my points of inflection occur? So my concavity changed from concave up to concave down when x was equal to -1 and when x was equal to +1. So this is a point of inflection. Okay, this is another point of inflection. But if I wanted to find the actual y value, what do we have to do? Plug in -1 and 1 into our function. Okay, but now using our second derivative, we can at least determine that at this x value and this x value, we have our points of inflection. So that's what it's called when our concavity actually changes on our function. We call those a point of inflection. Okay. More questions. In comparison to the original function, where does the tangent line lie when f is concave up? So let's think about this. When f is concave up, it's going to look like this. So when I draw a tangent line, except for their point of tangency where they're in the same exact point, the tangent line falls where? It falls under or lies under f of x. Okay, it is below f of x whenever your function is concave up. Because I know there's more questions here. Let me see if I can find them. No, where are they? Well, this is embarrassing. I thought they were here. Maybe they're on the next slide. Nope, they're not. Okay, well, there's supposed to be another question here that asks you, what about concave down? What about when your function is concave down? Oh, found it. What about when your function is concave down? Well, when your function is concave down, looks like this, and your tangent line lies above f of x. You're like, why do we care about this? Just, make a little note to yourself for later. Okay? I found the box. Let's see if I can... How does this affect, tangent line approximations? We actually, I think, have not done those yet because I kind of reordered things from last year to this year, and I'm realizing that at this moment in time right now. So you know what? We're just gonna say, hey, tangent line lies above or below depending on concave up, concave down. Sound cool? Great, wonderful. Let's keep on going here. Okay. Your turn. Determine the open intervals on which the graph of f of x equals x squared plus 1 over x squared minus 4 is concave up or concave down. Well, how on earth do we do this? What do you think? Again, you see where it says your turn? I would pause the video here at this point, give it a try, and then come back and see how you did. Okay? Since I want to know concave up and concave down, I got to look at my second derivative. Good job. Pat yourself on the back there if you got that right. This one's going to be fun. This one's going to be fun because it looks like we're going to have to use the quotient rule. Yes. I haven't done this one in a while. All right. Let's start with our first derivative. Okay. Quotient rule. Derivative of the top, 2x times the bottom, minus the top times the derivative of the bottom, all over the bottom squared. Okay, before I take my second derivative, I'm going to see if I can clean this up a little bit. I have 2x cubed minus 8x minus 2x cubed minus 2x over x squared minus 4 squared. I believe this turns into negative 10x over x squared minus 4 quantity squared. I'm going to take a step back / look at my notes from the past and make sure that I got, yeah, we're good. Okay, now that was your first derivative, my friends. Let's look at our second derivative. I know you're so excited. I can feel it. Even though I'm making this video in my classroom alone over the summertime, I can hear the excitement already building while you are watching this now. While I'm hanging out at home with my little one. It's going to be a great time. Let's see. So derivative of the top, negative 10 times the bottom, x squared minus 4 squared minus the top times the derivative of the bottom. So 2x squared minus 4. Don't forget about that chain rule. 2x all over x squared minus 4 squared. Oops. Squared, so to the 4th. Okay. All right. Before I simplify, what I like to do at this point is recognize that I have x squared minus 4 here, here, and here. So because I have it in this term, and this term, before I multiply out anything, I want to go ahead and reduce. One of those goes away, which means one of these goes away, and one of these will go away. Okay? So then I am left with f double prime of x is equal to negative 10 times x squared minus 4. I'll multiply that out in a second. Negative 10x to 2x over x squared minus 4 cubed. Okay, I intentionally didn't multiply that out so everybody could see what I did there, but now I do want to multiply it out so I can clean this up. So I've got negative 10x squared plus 40. Let's see, this is going to be plus 10x times 2 is 20x times another 2x, so 40x squared all over x squared minus 4 cubed equals 30x squared plus 40 all over x cubed. Nope. X squared minus 4 cubed. That is your second derivative. Okay? Referencing old notes. Yep, we're good. All right. To determine concavity, I need to find out where this is equal to 0. So I'm going to set this. So anytime you needed to know when a fraction is equal to 0, just look at the numerator. So 0 is equal to 30x squared plus 40. Okay? And then, let's see. I don't think we're going to get a solution here, guys, because you have negative 40 equals 30x squared. Then you're going to end up with negative 4/3 equals x squared. Oh, no. This has no solution. Okay. So that's interesting, because every time we've done this before, my points of inflection, or my possible values of my point of inflection, occurred when my second derivative is equal to 0. I wonder if there's any other weird thing happening on this graph that would make it change concavity, but not at a point. I want you to look at your function, okay? Look at it really closely. It's there, okay? There's something happening on your function. It's not at a point, but it's going to affect the concavity. It's just that we won't have an actual point of inflection. The concavity is going to change, but instead of at a point, maybe you've gotten it, maybe, we've got vertical asymptotes here, okay? Because you have a denominator, x squared minus 4, remember, you have vertical asymptotes, at x equals 2 and negative 2 when you set the denominator equal to 0. So even though I won't have a point of inflection where my graph changes concavity, my graph will still possibly change concavity over my asymptotes. So when I make my chart, I want to specify that that's what's happening. So I've got negative infinity to negative 2, negative 2. I've got negative 2 to 2, 2 to infinity. Okay, so then my second derivative is what I want to look at, but I also want to talk about what's happening on my original function. I think that'll help clear this up a little bit here. On my original function at negative 2 and positive 2, I have a vertical asymptote. So my function does not exist at negative 2 or positive 2, but I could still change concavity. Let's find out, okay? And also, if my function doesn't exist, if I have a vertical asymptote on my original function, coincidentally, here I still have a vertical asymptote on my second derivative because I still have x squared minus 4 in my denominator, and so I'm still going to have 2 and negative 2 not work in my denominator. So still vertical asymptotes, okay? All right, so let's plug in negative 3. Double prime of negative 3. Hopefully I can do some math pretty quickly here. Oh, actually, negative 3, you plug it in up top. No matter what you plug into the numerator, it's going to be positive because you're squaring it and you're not multiplying or subtracting by anything that's negative. So yeah, anything you plug into your numerator is going to be positive. So let's just focus on our denominator. So negative 3 squared is positive 9 minus 4 is 5. Cubed is so positive something. 125 over, yeah. So this one's going to be positive, which means my graph is concave up right here. Let's plug in 0. So if I plug in a 0 into my numerator, again, I'm looking at my second derivative here. Anything I plug in up here is going to be a positive. Okay, so this, I really just need to look at my denominator. So 0 squared is 0 minus 4. So it's going to be a negative. Cubed is still negative. So positive divided by a negative is going to be a negative. So that means my graph is going to be concave down. Okay, 2 to infinity. Let's look at f double prime of positive 3. Let's see. So positive up top. And it's going to be the same thing as putting in a negative 3 in the bottom. So it's going to be a positive in the denominator. So that's going to be positive. So then, since it's both positive, this is going to be concave up. Okay. What was the original question asking? Where is the graph concave up and concave down? All right, cool. We got it. F of x is concave up on, let's see, negative infinity to negative 2. Oops. Let's fix that a little bit. There we go. Union 2 to infinity, because f double prime of x is positive. F of x is concave down on negative 2 to 2, because f double prime of x is less than 0 or negative. Okay, so our concavity has changed at negative 2 and positive 2. However, these are not points of inflection because negative 2 and 2 are not points on my function. They're vertical asymptotes. So they're not actually points of inflection here. I hope that makes sense. Because your concavity is changing over an asymptote instead of at a specific point, they're not points of inflection. Okay, let's go on to the next slide. See what we got. Oh, speaking of points of inflection, if f of c is a point of inflection on the graph of f, then either f double prime of c is equal to 0 or f double prime of c does not exist at x equals c. Okay. Another thing that I like to add on here, if it's a point of inflection, yes, these two things are true. In order for something to be a point of inflection, f double prime of x must change sign. Okay? It is possible for these two things to be true and it to not still be a point of inflection. So the converse, remember we've talked about converse in the past here, so the converse of that statement is if f double prime of c is equals to 0 or does not exist at c, then c f of c is a point of inflection. Anytime I ask you this question, I feel like you guys are always like, she's probably asking because it's false. We just need to know why. Yeah, you're right. It is false. Why? Give me a counterexample. Oh, hey, Miss Reverend, the last problem we just did, we had a point, or we had two numbers. Let me go down. Two numbers where my second derivative didn't exist, okay? And my concavity still changed. The concavity changed, but my second derivative didn't exist. Well, that's because my function didn't exist. So be very, very careful with this, okay? Just because your second derivative does not exist, that doesn't make it an automatic point of inflection. You have to check to see that your concavity changes signs, but then you also have to make sure that it's an actual point on your function. Other situations where you could have graphically other situations, let's say you had, this function right here, where it comes up to a sharp cusp, okay? Concave up, sharp turn, concave up. Second derivative is not going to exist there because first derivative is not going to exist there, okay? So concavity, though, is still positive on both sides. So this is an example of not a point of inflection, but still a critical number, okay? Another good example is f of x is equal to x to the fourth, or any degree higher, any even degree higher than 4. Your graph looks like this. So then if you took the second derivative, you'd end up with x squared. Well, you would end up with 4x cubed for the first derivative, and then 12x squared for the second derivative. But your function, you would have your second derivative would equal to 0 right here, but you would still have concave up on both sides, so it would not be a point of inflection. It would be a possible point of inflection, but not an actual point of inflection. I hope that makes sense. Okay, so we've talked about points of inflection. Let's go back to, let's go back to this function right here. So remember how we determined where the graph was concave up and concave down? Okay, well now let's talk about, did that happen over points of inflection or vertical asymptotes? Here we knew that it was happening over points of inflection because -1 and 1 exist on our function. So sometimes whenever we ask for concave up and concave down, we might also say, what are the points of inflection? So to find the points of inflection for your function, you kind of already on to the right start here. You already know what x values. How do you determine the y values? We just plug them in. So we're going to say f of -1, f of -1. Oh, I had it handy and then I lost it. Hang on. Oh, here we go. Is going to be 1 over root e. F of +1 is going to be 1 over root e as well. So in the event that they ask you not only where does it change concavity, like what are the concavities, the intervals of concavity, if they also ask you to find the points of inflection, you would say point of inflection at -1, 1 over root e, and then at 1, 1 over root e. That's an e. There we go. Okay. So just real quick recap on that one. All right. So we've done a lot today. We've talked about relative extrema, we've talked about points of inflection. How does this all come together? Okay, so let's find the relative extrema for this function right here. I want you again to do the usual, pause, give it a try, and then we'll come back. Okay, we'll come back to it after, but you know, again, give it a try. So relative extrema, anytime I see this, I think critical numbers. Okay, that's my first instinctive go-to. So I'm going to say f prime of x is equal to negative 15x to the fourth plus 15x squared. Okay, I'm going to set that equal to 0. So 0 is equal to negative 15x to the fourth plus 15x squared. I'm going to take out negative 15x squared. So then I'm left with x squared minus 1. Okay, so then my solutions to this are x equals 0 and plus and minus 1. 0 from here, plus and minus 1 from here. Okay, prime of x undefined anywhere. No, this is a quartic function, so I have no critical numbers from this side over here. Okay, these are my only critical numbers. Okay, I want us to use the new tool that we talked about today. Okay, so to find our relative extrema, the first thing I'm going to do is try our second derivative test. Okay, so I'm going to make my chart using my critical numbers. Okay, I've got I'm going to go from negative infinity to negative 1. Ooh, that almost looks like a parentheses. Negative 1. And then I'm going to go from negative 1 to 0. 0 to 1. 1 to infinity. Okay. I'm looking at my second. I'm going to actually put all three of my functions here. My first, my function, my derivative, and my second derivative. Oh, that's beautiful. Look at how lovely that was. So let's start with, well, let's see. What order do I want to go in here? Let's go second derivative. Second derivative. You can do this any way you want to. Some people like to go function, derivative, second derivative. I just was trying to mimic what we did earlier today. So I have them all in, yeah. All right. So what do I know? Okay. I know that I have 0 here, here, and here. Because these numbers are my critical numbers. They came from the fact that my first derivative was equal to 0. So I'm going to go ahead and write those in. Okay. So then, let's see. I could determine my relative extrema using the first derivative test by plugging in numbers into my first derivative. But that's not what we're trying to do. We're trying to use a second derivative test. So in my second derivative test, I'm going to plug in my second derivative, my number here, strictly into my second derivative. Oh, I don't have that up here. Let's get that up here. F double prime of x. So if f prime was this guy, f double prime is going to be negative 60x cubed plus 30x, right? Looks pretty good. Okay, it's negative 60x cubed plus 30x. So then f double prime of negative 1, that's my first critical number, is negative 60 times negative 1 cubed plus 30 times negative 1. Okay, I don't necessarily care about the value. I care positive or negative. So negative 1 cubed is still negative 1. So negative 60 times negative, so it's going to be positive 60 minus 30, which is positive 30. That is a positive number, right? So because it is a positive number, let's think about this. Because this is a positive number, okay, that means my function My second derivative is positive -1. That means my function itself is going to be concave what? Concave what? Concave up. It's going to be concave up. So that makes this a relative minimum. Okay? It's going to be a relative minimum at -1. All right? If I wanted to check it at 0, I repeat the process. F double prime is 0. Well, that's pretty straight. Oh, no. I get a 0. Oh, man, what does that tell me if I get a 0? Does that tell me positive, negative, or anything? No. That means I have to still use what test here? The first derivative test. I have to still go back and use the first derivative test. Dang it, I was really hoping for a shortcut. Ah, my plans have been foiled. Well, I'm already here. Let's go ahead and do f double prime of 1. So negative 60 x, no, what am I doing? Negative 60 times 1q plus 30 times 1. So that's going to be negative 60 plus 30, so negative 30. Everybody see that? Did I do that math right earlier? I think so, yeah. So this is going to be negative, so that makes this a relative maximum because my function is going to be concave down here. Since my function is concave down, this is going to be a relative maximum. But that still begs the question, hey, what's happening right here? This is still a critical number. 0 is still a critical number. I have no idea what's happening here. But luckily, I don't have to do the full-fledged first derivative test. I only have to check it on this interval right here. So I'm going to do that in a different color. Okay, so I want to know what's happening from -1 to 0. So what's f prime of like -1/2? F prime of -1/2. So I come up here. Negative 15 times 1/2. That's a negative. 1/2 squared. Well, -1/2 squared is going to be 1/4 minus 1. That's another negative. So this part's negative. This part's negative. Negative times negative is a positive. So then I have positive right here. Okay. Let's do f prime of 1/2. Let's say this is going to be negative over here. This is going to be another negative altogether over here. So that's going to be a negative times a negative, which is a positive. Huh. It's positive on both sides. So even though we went back and we used the first derivative test, what happens here? I mean, it's positive on both sides, so that means it's increasing on both sides. So what's happening? Think about this. Anyone? There's no relative extrema here. This is a critical number, but no relative extrema. It doesn't happen. And that's okay. Sometimes it happens, sometimes it doesn't. Okay? As long as you followed your process correctly, you're good to go. So we have relative minimum. We have a relative minimum at -1 and a relative maximum, a positive one. I need to figure out what are those coordinates. So f of -1. I did some math in my head and I got 30. F of 1 is -30. Is that right? Am I looking at the right thing here? I'm not. I'm looking at my second derivative. I knew that didn't sound right. All right, so sometimes Murphin can do math in her head. Other times she looks at her old notes and the math she did in her head was incorrect. Let's see, so I can do this. -15 times, oh, that's just 0. F of 1 is also 0. Okay, so then f has a relative min at -1, 0. because f prime of -1 equals 0, and f prime of x changes from... No, I don't want to talk about f prime. Because I used my second derivative. See, you're going to catch yourself sometimes just like I did. But it's actually a little bit shorter. Watch this. And because f prime of -1 is 0, and f double prime of -1 was positive. Okay? Because I used the second derivative test for this, not the first. F has a relative maximum at 1, 0, because f prime of 1 equals 0, and f double prime of 1 was less than 0. Okay, I used the second derivative test for both of those. Now, I did still go back and use the first derivative test for the other critical number, but it was still not a relative min or max, so I don't need to bring that back up in my answer. I just want to know where the relative minimums and maximums are. Okay, so this was me using second derivative test. You don't have to use it every time. You can use first derivative test. It's just another way to go about this problem. Okay, let's see what else we got here. Oh, here's a fun little chart. I'm actually going to pause on this. Let me see what else I got here. Yeah, we're going to come back to this another time. I'm going to have this filled out for you a little bit later on, so just pause on that note. Okay. This problem, I'm going to do what I've done in the past, where I want you to find all the stuff on this one. Plug in your knowledge of first derivative test, second derivative test, all that good stuff, and then find your relative minimums, maximums, and concavity, all that good stuff. I will have the actual filled-in version on Canvas, but we're not going to go through that whole thing here because this video is already super de-duper long. Yeah, I'm not sure why that's there. All right, so I hope this helps a little bit with concavity and all that good stuff. Yes, I will put a recap of this problem on the board in Canvas, so just check that later. Again, if you are ever confused, check Khan Academy, Prof. Rob Bob, or your handy dandy textbook.